Hello, my name is Braeden Warnick, and welcome back to my short video series covering the ideas and development related to my thesis and the tech demo made alongside it. This will be my last video covering this project specifically, and it aims to offer a summary of everything covered in the written thesis that I will be defending soon. Now, using AI to drive the actions and behaviors of programmable agents or non-player characters has been a fundamental element in simulations and games for years. AI agents are vital in allowing engineers to visualize flow lines in real-life locations from their collective movements in crowd simulations, and they are just as vital in video games where the environment around the player is brought to life based on 3D models of NPCs acting in accordance with some form of AI system. In games, having NPCs that behave like real people is an often desired element to sell the illusion that the characters surrounding the player are alive, whether they are allies or enemies. However, the NPCs that are used in games require a fine balance of simplicity and complexity. I believe the key to creating NPCs that capture the simplicity that's found in the way real people naturally make decisions is using possibilistic reasoning in the behavior selection framework used by the NPCs. More specifically, I believe the key to designing NPCs that meet that fine balance of simplicity and complexity and can reason more like real people is by capturing the simple reasoning people naturally use in their day-to-day lives with possibilistic reasoning and combining it with a traditionally used planning framework such as hierarchical task networks. Possibilistic reasoning comes from the ideals of possibility theory, the most recent of which being the way to determine the possibility of an event, formalized by Dr. Schwartz at FSU. To summarize, this work states that the possibility for a real-world event is context-dependent, the context of which is defined as consisting of prerequisites that must be satisfied for the event to take place, and/or constraints that prevent the event from taking place. The degree of possibility of a future event can then be defined as a function comprised of the probabilities of the prerequisites occurring and the constraints not occurring. When the context of an event requires one or another prerequisite, then the possibility is equivalent to the probability of the prerequisite with the highest probability. Conversely, when the context of an event requires one and another prerequisite, then the possibility is equivalent to the probability of the prerequisite with the lowest probability. For example, if a student going out requires that they have enough time and enough money, and they have a probability of 40% and 70% for having the amount of time and money to go out, respectively, then the possibility of them going out would be the minimum of the two, therefore being equal to 40%. I believe this is intuitively more natural and human-like than other reasoning systems. This is because it offers a way to account for the base assumptions we as people seem to make when deciding how to go about our day-to-day lives. Now, although I believe using possibility theory as the basis of reasoning for decision-making in NPCs is the vital element in capturing the simplicity that is present in human-like decision-making, there still needs to be an overall system that this reasoning is used in. After some research, I found that the system I believe that offers the best foundation to mimic the overall process of human decision-making the most is hierarchical task networks, or HTNs. I'll explain why, but first I need to explain something else. I believe there are two fundamental elements in achieving a goal. First, one must define the possible paths of actions one can take in achieving that goal. Second, one must determine which path out of these is best to take based on the current state or additional information. People naturally apply this process to anything from getting chores done for the day, completing the next big work project, or figuring out where to spend your time and money for the night. I believe that possibilistic reasoning accounts for the second element in achieving a goal in the most human-like fashion in a clear, algorithmic way. But in order to account for the first element, I needed a system that can account for deconstructing an abstract goal into a direct list of actions that can be taken to achieve it. Although behavior trees offer a good system to deconstruct a method into sub-methods, I knew that in order to properly mimic the behavior of real people, the system required some method of planning, which led me directly to HTNs. These offer all of the same design benefits of behavior trees, but they also offer the AI agents or NPCs a concept of time, which allows them to step forward and consider the consequences of their actions to make the overall best decision. For this reason, I decided to use HTNs to account for the first element in achieving a goal, and for use in initially demonstrating how possibilistic reasoning can be used to drive more human-like behavior in NPCs. Now I'd like to talk about the example covered in my thesis that offers a clear demonstration of how possibilistic reasoning can be used in HTNs to drive the behavior selection of NPCs in games and simulations. To build on the previous brief example about determining the possibility of a hypothetical student going out at night, let's add some additional contextual elements to consider. The context for a student going out at night to a specific location includes more than just the prerequisites of the student having enough time and money. In this case, the possibility of the student going out additionally considers the prerequisite that they prefer that activity and the constraint of the customer traffic not being too high at the time of the decision. Using P1 as the prerequisite for sufficient time, P2 for sufficient money, C1 as the constraint for high customer volume, and P3 for personal preference for activity, when the contextual elements are combined, the equation for the possibility of a student choosing to go to a specific activity in their free time is the minimum of the probability of P1 and the probability of P2, and the maximum of 1 minus the probability of C1 and the probability of P3. This represents the student's need to have the required time and money, and that if they do, they should weigh their personal preferences against the current conditions for the available options. Now that a decision using possibilistic reasoning has been briefly explained, let me explain the HTN wherein this decision would be used. Consider the following HTN that represents the behaviors of an average student in a college town. Each hour, a student must consider their personal and surrounding world states to decide which tasks to perform during the next hour, or really any other segment of time if you want to use this for another system. Now the tasks selected by the student can be to either go to sleep, get food, go to school, go to work, or find a way to stay occupied. The task of getting food can lead the student to get takeout or cook at home. The task of staying occupied can lead the student to staying home or to spend money at any one of the predefined set of activities. In this example, these are going to a sports bar, going to a sports game, or going bowling. Tasks are generally selected by checking certain preconditions against the student's personal and world state information. However, the possibilistic decision replaces a precondition check in the stay occupied task when deciding how to spend their free time. This possibilistic decision can be represented with a utility selector that makes its decision based on functions that return the scores for the individual possibility values evaluated for each option. Using the possibilistic-based utility selector in only one branch of the HTN allows me to avoid any unnecessary additional runtime that can occur if one uses any type of sort to decide on a branch too much. In order to successfully develop a demo program that can show that the ideas presented in my work can be directly and easily applied to game code, there were several things that needed to be completed. The first was to create a base example demo that represented the core HTN, but with no possibilistic reasoning at all. This base demo was made to work solely on precondition checks and basic stats including money and hunger. Since no possibilistic reasoning was used, there was no reason to include stats for individual personal preferences or customer traffic at businesses yet. This meant that in the base demo, there was a simple amount of precondition checks that the student NPCs would consider when deciding how to behave. Students first check if they need to eat. The students spawn with a random hunger stat which decreases by a randomly assigned hunger decrease stat, and when the hunger stat falls below a predefined limit, the student decides their hunger and they seek out the best option for food. This food selection is based on if they can afford to go out, and if so, if the food location is closer than home. If yes to both, go buy lunch, otherwise go eat at home. After checking if they need to eat, the students check their responsibilities to make sure they don't need to be at either work or school. If the time of day currently falls between the hours in which the student needs to be at school or work, then they go to the respective location for the expected duration of time. Lastly, if the student doesn't have any responsibilities nor any immediate needs that need to be addressed, then the student decides on how they want to spend their available free time. With the base demo completed and the students properly acting in accordance with the previously explained core HTN, I needed to create a version of the demo that uses possibilistic reasoning. To do this, I needed to now add world variables to account for the customer traffic at each activity, and personal variables to account for personal preferences that will serve as the probability the student prefers each activity over the others. The customer traffic variable at each location changes depending on the time, and the values included were sourced from Google based on the traffic at similar locations around myself during times throughout the day. The personal preference stat for each student is based on two different variables that were added to the core student prefab object. The first variable for each preference stat is based on a variable that represents the preference for each activity individually. On spawn, a random float is generated and assigned to be the student's preference for each option for occupying time, including staying home. Then, another float is generated for all activities in general, and then for home by itself. This variable serves as a modifier that helps the student determine their desire to go out or stay in the first place. This modifying variable changes depending on the student's conditions, decreasing if the student gets off work or out of school late on the current day, or has work or school early the next. By combining these two variables, a total personal preference can be created for each individual activity option that the NPC can use when determining the possibility of enjoying any particular option. Then, since the base version of the demo used only the precondition checks and built-in priority order task selection in HTNs, I needed to replace the basic precondition check in the HTN that triggers the student's occupying free time with a utility selector that references possibilistic cost functions for its decision. Because the base demo already accounts for time and money in the precondition checks, the possibilistic cost functions were nothing more than comparing the preference against the current customer traffic for the future optional activities that the student is considering. As you can see, this manifests in the following code for the possibilistic cost function for going to the sports bar. The possibility of enjoying the sports bar is the maximum of 1 minus the world manager bar traffic stat and the total personal preference for going to the sports bar. And since there is no customer traffic at home, the possibilistic cost function for the option of staying home is simply just the personal preference variable that represents the probability that the student prefers staying home over the other activities. With these additions included and successfully integrated, the behaviors of the NPCs started to more realistically reflect the behaviors expected of students in such a virtual environment. To help emphasize what the successful integration of possibilistic reasoning accomplished, I'll now cover the emergent behaviors that appeared in the possibilistic demo and how they differ from the simple behaviors present in the base demo. Since the core of the different HTN domains was more or less the same to cover the basic responsibilities, the most glaring difference between the two demos was that students seemed much more active in their free time in the base demo than in the Possibilistic demo. The student NPCs operating based on the Possibilistic domain were much more balanced in their choices for how they spent their free time, with a significant amount often choosing to stay home rather than go out and spend money on an activity. Comparably, the overall traffic and behaviors expressed by the student NPCs operating on the Possibilistic HTN domain were more expressive and realistic. The base demo sees all students that are off and out of class go out on the same night as they all gain enough money to afford to do so. However, in the Possibilistic demo, there is an average amount of foot traffic at each of the activities, while the rest of the student NPCs remain home due to their preference consideration. The Possibilistic student NPCs represent a more realistic simulation of foot traffic on an average night in a college town, since every student is able to consider both personal preferences for how often they go out and how much they want to stay in on a specific night, rather than just be immediately compelled to spend money as soon as they have it. Besides the obvious differences in behavior trends between the two demos, there is one distinct emergent behavior I want to bring to attention. One that has been mentioned in my previous video, but was by far the most interesting difference I observed while watching these demos run over time. Student NPCs would often head home after work because the business traffic at the activities were mostly higher than average around those times in the demo. If the student's preference for the activity wasn't enough to outweigh the traffic, then chances were that their home preference would lead them to head home, often staying there for the night. But sometimes there would be a few students who would then leave their homes around 8 to 9 p.m. to go do their preferred activity. During initial demo testing, I originally thought that the domain or my code was dysfunctional, but I later realized that this buggy behavior was in fact completely reasonable on behalf of the student NPC's perspective. Their home preference would just outweigh their preferences for other activities, especially during points of moderate to high customer traffic. So, after work or class, as soon as they were free, they'd just go home. However, as the night would go on and the customer traffic would die down, the student would reevaluate the possibility of spending their time at home, and then they would decide that going to a less busy activity would be better than staying home. This is the perfect example of the possibilistic reasoning being used to create emergent and expressive behaviors, since this behavior is only caused by the comparison being performed by the possibilistic cost functions in the utility selector. Now that I've summarized the ideas and work completed in my thesis, I'd like to cover the three main ways in which I hope to expand on my research in the future. The first is to propose an AI framework for groups of NPCs that considers possibilistic reasoning when deciding tasks between AI agents. Possibilistic reasoning and group HTNs will allow for groups of NPCs to account for the human-like assumptions we make when making decisions and will enable the decision and development of more human-like group behaviors. This is beneficial since creating more human-like group behaviors would greatly benefit both video games and crowd simulations. Whether developers are trying to create an AI system for squadrons of enemy NPCs that the player has to fight against, or for companion NPCs that support the player in systems where they help complete objectives, more human-like reasoning helps sell the illusion that the player isn't just playing alone with bots. Additionally, modeling groups with this framework will allow for crowd simulation software to use possibilistic reasoning in their virtual groups of AI agents to model how they navigate and achieve objectives. More human-like behaviors is important for crowd sims to help create more realistic visualizations of venues, whether they're stadiums that want to model the behaviors of a couple at a sports game, or an amusement park modeling the behaviors of families. The second goal for developing my work in the future is to expand the research to help alleviate some of the work done by AI designers and developers that choose to adopt this framework. One big issue with HTNs, my framework included, can be the amount of time it takes to design them, especially if you want them designed well. One recent proposed solution for helping with this issue is an HTN learning algorithm that was proposed in the paper Automated Learning of Hierarchical Task Networks for Controlling Minecraft Agents. To develop my work further, after applying possibilistic reasoning to group HTNs, I'd like to explore how I can adapt the proposed HTN learning algorithm to possibilistic HTNs specifically. Adapting the algorithm to work with possibilistic HTNs will reduce the human design time for those using this framework since they'll be able to construct them from collected data. The goal of being able to construct HTNs from collected data is so that AI designers can simply tweak an HTN built from the data as needed rather than build it entirely from scratch. If successful, developers could have real people play their single-player or multiplayer games and then use the traces from their gameplay data in order to build HTNs for whatever bots that are needed. This would offer developers a quick way to create NPCs that depend on possibilistic reasoning, using nothing more than data recorded from playtesting. Similarly, developers could construct HTNs for AI agents and crowd simulations of certain venues, creating game traces from smart security camera footage in the locations of points of interest. Or, stores like Walmart can create them from using similar camera data, combined with the individual customer account data available from the mobile app that the customer uses to track their budget while shopping in store. My last goal is simpler than the other two, but still important in helping develop this work further and to spread the use of this proposed framework. Besides accounting for more in-game situations by applying the framework to groups, or helping to alleviate the design drawback of using this framework, I'd like to create a demo example in Unreal Engine to help show how the ideas translate to Blueprint and C++ coding. This may be considered less significant than the other two goals, but my original demo was made in Unity, and it used a third-party HTN library, so applying these ideas to all game code may not be entirely clear. Providing a clear example of how the ideas can be used in Unreal would be vital in helping spread the adoption of this framework, since it would make it easily understandable and accessible for the large percentage of game developers that also use Unreal. To summarize, I'd like to address the contributions I believe this research makes to HTNs and possibility theory. First, although HTNs aren't the most common AI system being used in games today, I believe this work helps advance the area in cases where HTNs are used and a section of the domain is using a utility selector. In these cases, this proposed framework and demo offers a great example for future developers looking to account for personal preferences and world variables in their cost functions easily. Not only does possibilistic reasoning make the logic and overall readability of complex decisions easier to understand, but since the possibilistic functions operate on combinations of simple min and max functions, they can end up running much faster than some more complex mathematical functions. Also, although designers can design traditional HTNs with the same level of expressiveness, creating expressive and believable NPCs with this proposed framework has proven to be simple, with only requiring minimal adjustments to a simple base HTN because of the use of the possibilistic cost functions. This paper also makes a significant contribution to possibility theory by proposing another application of using the ability to compute the possibility of a future event. The application is in the form of a proposed framework that can be used to drive the behavior selection of various forms of AI agents in video games or crowd simulation. Besides just using the possibility of an event to determine the best route a truck can take on the way through a network like in related work, this paper establishes that possibility theory can be abstracted to be used in another form of network, more specifically HTNs. This opens the door for possibilistic reasoning to not only be used in video games or other virtual simulation, but any other situation that relies on navigating a network of choices. In conclusion, this research proposes an easy-to-understand framework that integrates possibilistic reasoning into hierarchical task networks. The goal of this framework is to offer AI designers and developers a structure for developing behavior selection systems that can be more expressive and human-like in reasoning than comparable systems, while at the same time being easier to design and understand. Assuming that HTNs do model human planning better than comparable methods like GOPE, and that using the possibility of an event to make choices models human decision-making more closely than probabilistic analysis or other mathematical functions, then it would stand to reason that a system made from the successful integration of the two would be one that can more accurately model human behavior selection than some other comparable systems. Beyond achieving this goal, an example was designed and given alongside a successful software demo that was implemented in Unity. All that has been covered up until this point serves as a summary of most of my written thesis that can be found in the description below. Not all the details have been explained here, but if you're interested or if you'd like more explanation about my ideas, their related work, or my demo implementation, please feel free to check out and or share the links below. This will be the last video covering the development of my thesis work and the accompanying demo. As of publishing this video, I will be scheduling my thesis defense to take place by the end of March, and assuming all goes well, then I will be graduating at the end of April. Besides preparing for my defense, I'm also in the process of applying for any and all available game AI or game R&D related positions. So, if you're watching this and know of any possible opportunities, please don't hesitate to reach out to me on my LinkedIn or through the email below. Thanks for watching.